Your chatbot confidently tells a customer your return policy is 90 days. It's actually 30. Then it describes features your product does not even have. That is the gap between a great demo and a real production system. Language models sound certain even when they are wrong, and in production, that gets expensive fast. You lose users, waste API credits, and face compliance liabilities. This is why serious engineering teams use Retrieval-Augmented Generation, or RAG. It pulls in relevant, current information from your own databases, grounding the model in verifiable facts found in your specific documents. But RAG is not a single off-the-shelf solution. There are dozens of distinct architectures, each solving a different problem. Pick the wrong one and you waste months of development. Make the wrong architectural choice and you will bankrupt your cloud compute budgets, wreck your response latency, or fail to stop false information reaching users. Every developer faces the exact same trade-off: optimizing for architectural efficiency versus handling query complexity. To navigate this, we use this chart. It maps the exact implementation and latency costs on the x-axis against query complexity and accuracy on the y-axis. We are going to plot the 9 core RAG architectures onto this matrix to determine their true return on investment for your specific project. Over-engineering a simple task or under-equipping a high-stakes search kills AI projects faster than a weak foundational model. We start with standard RAG. This is your baseline lookup mechanism for low-stakes environments. This diagram shows the process. You chunk text documents into segments, vectorize them, and run a rapid similarity search to pull the specific data you need. It drops right into the bottom left of our matrix. It delivers sub-second latency and extremely low compute costs, but it treats retrieval as a simple one-shot lookup. If a user asks a vague, multi-part, or follow-up question, the system grabs irrelevant text and floods your output with noise. To fix that context blindness, developers add conversational RAG. This adds a memory layer that stores the last 5 to 10 turns of the chat. If a user asks, "How much does it cost?" the system looks back at the history to figure out what it refers to before searching. That extra query rewriting pushes it slightly higher on both axes. You pay higher token costs and run the risk of memory drift, where irrelevant topics from 10 minutes ago pollute your current search. Now, these baseline architectures are incredibly fast. However, they mathematically assume that the user's query and your internal retrieval engine are both flawless. When you move into healthcare or finance, those baselines fail. Here, accuracy is a matter of liability. This is the workflow for corrective RAG, or CRAG. A lightweight grader model evaluates internal documents. Correct documents pass through, while incorrect ones are discarded, triggering a fallback search to the live web. Bridging your internal data with verified, fresh external facts drastically cuts down on hallucinations. But look at the matrix. Adding that grader model introduces a massive 2 to 4 seconds of latency and racks up external API costs. If you want the system to critique its own reasoning autonomously, you use self-RAG. The model generates special internal reflection tokens. If it realizes a retrieved document doesn't actually support a claim it just made, it pauses, re-retrieves new data, and self-corrects mid-sentence. Achieving that requires highly specialized, fine-tuned models.
It lands in the extreme top right corner, bringing maximum factual groundedness along with extreme computational overhead. Enforcing absolute truth forces you to sacrifice speed. These tools are heavily resourced and far too slow for fast, consumer-facing chat. Another massive variable is the human on the other side of the screen. Users are notoriously bad at writing clear search queries. Fusion RAG is the brute force architectural solution to poorly phrased prompts. It takes a single vague prompt, generates 3 to 5 variations of it, and runs parallel searches across your database to guarantee high recall. It sits in the middle right of our matrix because it multiplies your vector search API costs by up to 5 times and adds latency from the complex re-ranking math required to sort the results. Hide offers a counterintuitive, conceptual alternative to that brute force approach. Watch this process. Hide prompts the language model to write a hypothetical or fake answer first. It then uses that generated text to find real documents in your database that match that fake text. It bridges semantic gaps brilliantly for vague concepts. But if the fake answer is completely wrong from the start, it misleads the entire search, introducing a severe bias risk. These prompt expanding techniques salvage bad human inputs, but they artificially inflate your system's workload and API costs to do it. Finally, we reach the heavyweight architectures, engineered for maximum scale and complex reasoning. This router diagram illustrates adaptive RAG. It sorts queries by complexity, sending simple questions down a fast, direct path, and routing hard analytical questions through a looping, multi-step search. Matching your computational effort to the query's complexity yields massive cost savings. But if the router misclassifies a hard question as easy, the system fails to search properly. Agentic RAG takes this further. It replaces simple retrieval with autonomous agents that orchestrate web searches, internal APIs, and complex tools on their own. It handles multi-step logic beautifully, but it carries the highest latency and expense. Using this for simple FAQs is complete overkill. Then there is GraphRag, which abandons semantic text similarity entirely in favor of explicit relationships. It models knowledge as distinct nodes and edges. By tracking exactly how entities influence each other, it can hit near 99% accuracy for causal, multi-hop reasoning. Both GraphRag and Agentic RAG dominate the high-cost, high-complexity sectors of the matrix. GraphRag requires enormous upfront data engineering and creates a rigid structure that is difficult to update. These heavyweights offer incredible theoretical power, but their latency and engineering demands will bankrupt projects that don't truly require them. Over 1,200 RAG papers were published last year. Chasing academic complexity for a basic app is like driving a sports car through a grocery store. This tree maps constraints to architectures. Budget constraint? Start with standard RAG. Complex architectures just mask garbage data anyway. Managing scale? Adaptive RAG balances sub-second latency with complex edge cases. Zero hallucination tolerance? Invest in corrective RAG or GraphRag to prevent liability. Keep in mind, modern production systems rarely use just one architecture. You will likely blend them, pairing fast standard retrieval with a corrective fallback for low-confidence answers. The most effective RAG system reliably serves your users within the strict constraints of your cloud bills and latency limits.